Hello learners, welcome back. Let's understand what is torsion. Torsion is another form of movement which causes twist. And here I have shown a shaft which is under torsion or torque, and it is represented by a double arrow. Now what does it mean? It means that if you put the thumb of your right hand in the direction of the arrow, then your fingers will curl around the direction of the twisting. That means the torque is in this direction. Now while twisting, the cross section of the torque remains constant. That means the circular portion remains circular and it will not change. Then what will change? The angle about of the twist will change. Let me explain what is that. So if I draw a line something like this, which is, let's suppose, AB, this line AB will become something like this. Let me call this AB dash. This is point A and this was point B. So point B will move from B to B dashed. This is the meaning of torsion. This will change the point B from B to B dash. Now there will be a formation of angle. Let me call this angle phi. This angle phi is shear strain, and let the length of the shaft be L. Now what will happen in the circular section? This point B, when it moves from B to position B dash, it will form an angle at the center of the circle. This angle, let me call this as angle theta, is known as the angle of twist. Let me write it here. Angle theta is called the angle of the twist. Angle of twist. Now, if we look carefully over here, suppose this is point B, this is point B dashed, and so this is point B, this is point B dashed, and this is the angle of twist, angle theta, and it causes a shear stress in the shaft. And now this shear stress is maximum in the outer periphery of the shaft and is zero at the center of the shaft. So it is a linear function of the radius of the shaft, right? Let me call this as tau, and this is tau max. That means the shear stress is maximum at the outer periphery and it is zero at the center of the shaft. Let this distance be small r and the radius of the shaft be capital R. From the center to here it is capital R. So let me write it down. From the center to the outer periphery is capital R. Now let's imagine a small area dA here at the radius r from the center. This is small area dA. Now what will be the torsion? The torsion will be equals to integration of shear stress at the area into area. It will give us the force, and force must be multiplied with the lever arm in order to get the moment, and torsion is nothing but the twisting moment, right? So this tau into dA will give us the force, multiplied by the radius small r will give us the torsion. Now look here, from similar triangles we can say that in this figure, from similar triangles we can say that, suppose this is tau max. I'm drawing it again. This is tau max. This is the center of the circle. This is tau. This is small r, and this distance is capital R. Now from similar triangles we can say that tau max by capital R is same as tau by small r. Now in place of tau we are replacing it by tau max by r into small r, right? So torsion we can write it as tau max by capital R into small r square into dA. Now this maximum shear stress and capital R is constant. So we will take it out of the integration, and it comes out to be tau max by r integration of small r square dA. Now this quantity small r square dA, integration of this is nothing but the moment of inertia. But this moment of inertia is polar moment of inertia. It is polar moment of inertia. But it is denoted by either IP or J. You will find both notations. So this torque is equals to tau max by R into, I'll write IP, and rearranging we get P by IP is equals to tau max by R. Now this is one of the equations which is very important. Again, let's focus over here. This angle phi is the shear strain, and also we know that BB dash, which is this arc, is equals to phi into L. Am I right? Also BB dash is equals to theta into R. This angle of twist into radius of the cross section of the shaft. This is capital R. Now from equations, these two equations, let me call them equation number 1 and equation number 2, what we get, phi into L is equals to R into theta. Now from Hooke's law, we know that tau is equals to rigidity modulus into shear strain. Now I am writing rigidity modulus as C. You will sometimes find it as written as G also. So phi can be written as tau max by rigidity modulus. Now replacing this rigidity modulus by tau max by C, we get tau max by C into L is equals to R theta, or we can write tau max by R is equals to C theta by L. Let this be equation number B, and let this be equation number A. So from equation number A and B, we can say that T by IP is equals to tau max by R, and from equation number B, we can say that tau max by R is equals to C theta by L. So the complete equation for the torsion is T by IP is equals to tau max by R is equals to C theta by L. Now, if you take any other point instead of the periphery of the circle, that means if you take any other arbitrary point from the center of the circle whose radius is small r, and here the shear stress is tau. So let me draw the stress profile again. It is tau max over here and it is tau over here. So you can write T by IP is equals to tau max by R is equals to C theta by L, and that is equals to tau by small r. So hope this helps. This is one of the most important equations in torsion, in strength of the materials. So with this is Shraddha Bharti signing off. Bye bye and have a nice day. Do like and follow me for more.